distinct linear factors. So if you have a fraction or a rational expression that's factored this way, right? They have to give it to you factored, or you have to factor it. So let's pretend that we already factored it just to save time and space. Since these are linear and distinct, meaning they're both unique and different factors, right? You can separate them or decompose them as a over the first term plus b over the second one. All right, so imagine if there's an integral here. This one might be a pain, but these two would be just ln integrals, right? That's where we're headed. Case 2. Repeated. Linear factors. So let's say you factor the bottom, right? And you ended up with x times x minus 1 squared. So you see how this has a square on it. So we consider that to be a repeated factor, right? Because it's x minus 1 times x minus 1. But x times x minus 1, those are considered to be distinct from each other. It's just that the x minus 1 has a repeated is a repeated factor because of that power. Okay, so you still do a over the first one plus b, and then this is where it changes, b over the next one. So you count up until that power. So you go up to 2. See what I mean? So if this was a cube, you would do it 1, 2, 3. Since it's a 2, I do 1, 2. So you could put the 1 there just for emphasis. Does that make sense? That's case 2. Case 3, distinct quadratic factor. So if you can't factor it, and you have to just go ahead and use it as a quadratic factor here, such as this example 3, case 3. Let's say you have x over x minus 1 times x squared plus x plus 1. So this cannot be factored. They're both distinct, but this one cannot be factored. So you have a over the first one plus, and this is where it changes. So you add bx plus c over the quadratic term that doesn't factor. Okay? So that's case 3. And I'll remind you on how to solve for A, B, and C when we start the actual questions. Right now, I want you to remember the setup. Remind you of the setup. Repeated quadratic factors. So let's say you have something that doesn't factor, but it is repeated twice or 3 times, whatever. Let's make it 3 just for fun. Let's say the bottom is x squared plus 4 cubed. So since it is cubed, you got to do it 3 times. So ax plus b over the first one plus cx plus d over this one squared plus ex plus cdf cubed. So you see how we went from 1, 2, 3. Does that make sense? So we're applying the repeated rule onto a quadratic type factor. Case 5 is the most annoying one because you have to do long division in order to fix it, which will probably require an entire page. Case 5, the irrational expression is an improper fraction. So basically, if the degree of the top is bigger, we consider it to be improper. So for example, let's say you have x cubed minus x plus 3 over x squared plus x minus 2. So if that happens, you're going to have to do long division. Do you guys remember how to do your long division?
Barely.
Yeah, let's review it then. Over here, I'm going to show you. Well, let's do the old school one, right? Yeah, I know this sounds silly, but it will help. So 5 goes into 5 one time. The algorithm says you do 1 times 5, right? That's the pattern. And then you put a minus on it. You subtract. Then you bring the 9 down, right? 5 goes into 9 one time. 1 times 5 is 5. Then you put a minus on it. So the pattern is what matters. We got to multiply. You got to put the minus. So we're going to be doing the exact same thing. The numbers don't matter. But this pattern matters. You get the 4, and then you bring down the 5. 5 into 45 is 9. 9 times 5, and then you do the minus again, right? So it'll be very similar to what we just did here on this question. So the only difference is you only divide by the first term. Okay. So you take the x squared and I divide that into this first one. So I'm only going to use this for my division. So x squared goes into x cubed how many times? Right, so you do x cubed over x squared, that's x times, right? And then the pattern says x times all this stuff gives me this. Right, x times x squared is x cubed, x times x is x squared, x times negative 2 is negative 2x. So you have to swap all the signs because you're going to subtract it, just like we subtracted the 5, right? So this is a 0, negative, oops, I made a mistake. Let me fix something. So the rule of thumb says, before we do this step, we'll redo that in a second. The rule of thumb says that we have to put a placeholder so it doesn't get confusing. Not that we have to, but it helps. There is no x squared term, so we should put it ourselves. So x squared goes into x cubed x times, and then we multiplied it. So we got x cubed x squared negative 2x. So subtract them. So this is a minus now, minus plus. So this is 0. 0 minus 1 is negative 1. Negative minus 2, oh sorry, negative plus 2 is 1x. Bring down the 3. Okay. Now we start over, start the pattern again. Just like when we got to here, 5 went into 9 one time. X squared goes into x, negative x squared, negative 1 times, right? So it'd be, actually it was positive, like this. Okay, so negative 1 times all this would be negative x squared minus x plus 2. But then I got to swap all my signs. So 0 minus x plus, that'll be 2x. 3 minus 2 is 1. So this is my remainder. So this fraction becomes x minus 1 plus 2x plus 1 over the divisor. That's how we write fractions. So if we were integrating this, which is a pain, you would integrate these pieces instead, right? You may have to do partial fractions on this part, right? So you would say, okay, well, that becomes 2x plus 1, x squared plus x minus 2. That does it factor? No. So that would be equal to ax plus b over this. Yeah, I don't think it'd be worth it. Yeah, no, that doesn't, that's pointless. Oh, it does factor. Stupid. This is minus 2, right? So that would be x plus 2, x minus 1, right? So you would use a over x plus 2 plus b over x minus 1, right? That's the ugliest x I've ever written. So we use the rules from the first 4 cases. This is a over the first factor plus b over the second factor. Does that make sense?
Yes.
All right, so that's a quick rundown.
What was that answer that's at the very top? Is that x minus 1 plus 2x plus 1 over x squared minus x, or x squared plus x minus 2?
Yeah.
Okay.
All right. Okay, so it's a quick rundown. I mean, maybe a little too quick of what are the cases for partial fractions. So we're going to go ahead and start the 8.5 section, and we're actually going to solve for a, b, c, whatever the heck they asked for, and then integrate. Okay, so let's go ahead and do that. So 8.5, continue. So first step is, this is just a quick summary. Divide when improper, so that's case 5. In that sheet that I gave you. Number 2, always factor the denominator. Linear factor, let me write that better. It just looks ugly. linear factor decomposition. Okay. So the integral is the first example of 1 over x squared minus 5x minus 6 dx. So what we're going to do is deal with this fraction and separate it, because that would be 1 over what, x minus 6, x plus 1, which is equal to a over x minus 6 plus b over x plus 1. So what you have to do is multiply both sides by this denominator to cancel all the fractions, and then you start equating the coefficients to find a, b, etc. So I'm going to multiply both sides by this here. That's how you solve for a and b. Right? So you see how we take this equation, multiply both sides to cancel all the fractions. So these will cancel, leaving me with the number 1 equal to x minus 6, x plus 1, x minus 6 plus x minus 6 times x plus 1 times b over x plus 1. So these fractions are now gone, leaving me with 1 is equal to x plus 1 times a plus x minus 6 times b. So at this point, you could technically so there's 2 techniques. One's called the Heaviside method, where you can let x be whatever you like to cancel this. That method only works sometimes. In this scenario, it's the easiest method, but I'm going to show you how to equate the coefficients so you know the way that always works. Okay, so what you do is distribute everything. Distribute everything. Group everything together that is the same. So by same, I mean like same degree. So ax plus bx plus a minus 6b. So all the x terms, all the constants. And then you create a system by equating the coefficients. So there is no x term on the left. So the x terms will be equal to 0 because there is no x over here. So you take the coefficients and equate them to the coefficient on the left. Coefficient of the x over here is 0, therefore equal to 0. And then you do the constants. There's one constant, right? So you put 1. So solve the system, right? You use a matrix, use whatever you want, doesn't matter. You'll get, let's see, you'll get a equal to 1/7, b equal to a negative 1/7. once you do your work. So basically what you do is create this new integral. So you integrate 1/7 over x minus 6 dx plus the integral of negative 1/7 over x plus 1 dx. So see how these are easier? So you'll have the integral. You can just pull out the 1/7 because it's just in the way, right? Of dx over x minus 6 minus 1/7 dx over x plus 1. So this becomes 1/7 ln of x minus 6 minus 1/7 ln of x plus 1 plus c. I'm sorry, it wasn't on the screen. Do you see how the partial fractions make the integral more actually possible? Any questions on this first problem? Do you remember the partial fraction technique? And do you see how the integral came about?
For the most part.
Okay. Let's do another one. All right, where is it? Oh, here we go. Example 2. So integrate 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x dx. So if you factor the bottom, you should end up with x times x plus 1 squared. Top part stays the same. All right, so we're going to use the, we don't need to write the integral because we're going to do the partial fraction first. So save us some writing. So that would be equal to a over the first one plus b over the second one plus c over that next power. So you're going to multiply this denominator on all these fractions, right, to clear the fractions. So on this side, I'm going to skip the little step just to save space. You're going to end up with just this denominator, right, because the other part will cancel. So multiply x times x plus 1 squared times a over x plus x times x plus 1 squared over x plus 1 plus x times x plus 1 squared times x plus 1 squared. Okay, so as you can see, the x will cancel, one of these will cancel, all of these will cancel, leaving you with 5x squared plus 20x plus 6, which is equal to x plus 1 squared times a plus, sorry, I forgot my b, didn't I? X times x plus 1 times b plus cx. So expand this and equate the coefficients. Okay, so here we go. So that'll be x squared plus 2x plus 1 plus bx plus b plus cx. Distribute, and then we will equate the coefficients. Let's see here. So we get ax squared plus 2ax plus a plus bx plus b plus cx. There's only one x term, so I'll write that by itself. All the x terms will be together. All the constants together. Okay. So here we go. There's only one x term, so a will equal to the coefficient of the quadratic. So that's your first equation. Now all the x terms, a, b, c, is equal to 20, because that's the x's equal to the coefficient of the x. Right, that's where this comes from. Then the constants, a plus b is equal to 6. So a is 5, so that was given to us nicely. If a is 5, then b has to be 1. If a and b are 1, c has to be 9. Wait. Hold up. Let me double check everything. Sorry, got lost in thought there. So that would be, so plug in the a and b and see what's going on here. So 2 times 5 plus 1 plus c is equal to 20. So 2 times 5 is 10 plus 1 is 11. Subtracted over c is 9. Yeah, that's right. Okay. All right. So you got A, B, C. Just plug them in, and then we can integrate. So we're going to integrate 5 over x dx plus integral of 1 over x plus 1 dx plus 9 over x plus 2, oh, x plus 1 squared dx. So now that we've done the partial fractions, we plug in the a, b, and c. That goes here, right? And then integrate. So we'll get 5 ln x plus ln of x plus 1 plus 9. Actually, that's not ln, that'll be a u sub. That would be what? That'll be negative 9 times 9 over x plus 1 plus c. Anyway, does that make sense? The main idea?
It's starting to.
Yeah, so we're separating the ugly fraction into multiple fractions and then integrating these instead, right? Integrate these guys instead. Okay. One moment. All right. Let me find a good one here. Okay. I guess let's do this repeated root problem. Okay. Example 3. Integral of 8x cubed plus 13x over x squared plus 2 squared dx. All right, so we will do our partial fractions on this guy, and notice that it is a quadratic that can't be factored. So we're going to write ax plus b over the first one because it's repeating, plus cx plus d over the next one. So equate the so cancel the fractions and then start equating the coefficients. So multiply both sides by this LCD. Left side will always end up with just the denominator. Sorry, the numerator. So these two multiply by x plus 2 squared plus same thing on the next one. And so these will cancel completely. This will cancel one of them, leaving us with 8x cubed plus 13x equal to x squared plus 2 times ax plus b plus cx plus d. So at this point, you have to expand everything and equate the coefficients. Okay. So on this side, it just stays the same. Over here, we get ax cubed, so x squared times ax, x squared times b. Just FOIL this out. Plus 2ax plus 2b plus cx plus d. So once everything's expanded, group everything that is the same degree. So the cube, the quadratics, there's only one of each, the x terms, the constants. So a is equal to this constant, 8. B, there is no quadratic term, right? That means b is 0. The x terms, we have 2a plus c equal to 13. The constants, well, b is 0, so that part will be easy. 2b plus d, there is no constant. That means that d is 0. So we got a, we got b, we need the c, d is 0. You see that? Equate the coefficient for the cubic. A is equal to 8. There is no quadratic for the b, so b is 0. The x terms are equal to the x term. Constants are equal to the constant. There is no constant, so if b is 0, then d has to be 0. Right? That's what where that came from. All right, so if a is 8, plug that in here, it'd be 16. C would be what? -3? Is there any questions so far?
Yeah. In this particular, which case was this problem?
This one's the repeated quadratic. I think it was number 3 or 4. Let me see.
Oh, okay. It was case 4.
I think so. Let me see. 4. Right. It was case 4 for the partial fraction. The only difference now is on the when we went through the cases, all I did was set them up. So now we're solving for stuff. We're actually finding ABC.
Okay.
So there they are. Luckily, this is gone, right? So we have 8x over x squared plus 2 plus negative 3 over x squared plus 2 squared. So there's the stuff we're going to integrate, these two here. So the answer to this question will be the same as the answer to this guy. So the integral of 8x over x squared plus 2 dx minus the integral of 3 over x squared plus 2 squared dx. Oh, shoot. I forgot the x right here. Okay. So we will have to do a u sub. I guess, yeah, for both. So let u equal x squared plus 2. Du will be 2x dx, right? Du over 2 is equal to x dx. So if I were to rewrite this as 8 over x squared plus 2 dx minus 3 integral x over x squared plus 2 squared dx. Do the sub and we'd end up with 8 integral of 8 du over 2 over u minus 3 du over 2 over u squared. So the integrals would end up being what? 4 ln u. Integrate this guy, and that would be plus 3 halves u the negative 1 plus c. So the final answer would be 4 ln of x squared plus 2 plus 3 over 2u plus, oh shit, I should change that back. Over x squared plus 2 plus c. So this would be our final answer. Are there any steps that don't make sense? Okay. You guys have any homework questions you've been struggling with in chapter 8? Okay, then we'll finish chapter 8 next time, and then we'll talk about the next exam date / review on Thursday. We'll talk about it. If you have any questions, we'll call it a night here. I want you to try this out for a bit before we start the next stuff, because this is really algebra heavy and I need you to practice. And if you're comfortable, then great. And if you're not, please bring questions on Thursday. Okay.